Yeah, hi everyone. This video is about PCIe Gen 5 MAC layer functional verification. So this is our test bench environment. So here our RTL is PCIe MAC layer. So we configure RTL into two devices. One is upstream device and another is downstream device. So upstream device will act like a upstream port, downstream device act like a downstream port. So our DUT has two interfaces. Our DUT has two interfaces. One is low power low power interface. So this is DLL and pi layer interface. DLL and pi layer interface. This is DLL and pi layer interface. And other side we have the pipe interface. Other side we have the pipe interface. This one is upstream port and this one is a downstream port. So for downstream port also we have link layer interface, low power interface. So this is DLL pi interface, DLL pi interface, and we also have pipe interface. We also have pipe interface. So DLL side we have UVM components like receiver passive agent, transmitter active agent. So and we have LTSSM active agent. And on the pipe interface we have receiver slave and a transmitter slave and LTSSM agent. So same components we have for the downstream device also. So downstream device link side, data link side we have transmitter master, TX master agent, active agent to simulate the transaction layer and data link layer behavior. So to simulate the transaction layer, data link layer behavior, so it will generate TLPs and DLLPs. This one generate TLPs and DLLPs. And receiver passive downstream agent will handle incoming TLPs and DLLPs. Incoming TLPs and DLLPs. So same way upstream side also. Transmitter master agent will generate TLP and DLLP traffic and receiver passive agent will consume the incoming TLP DLLP traffic. And we have the transmit slave for upstream, receive slave for upstream, transmit slave for downstream, receive slave for downstream. So the slave devices will monitor order set flow through the link and it will predict the next LTSSM state. So transmitter slave and receiver slave will predict the next LTSSM state. Same way for downstream side also. So for pipe interface we have RX slave downstream, TX slave downstream. See these both components will monitor the order set flow through the link and they will predict the next LTSSM state. They will predict next LTSSM state. And this is about TX and RX slave devices. And here uh, link interface side we have LTSSM2 for upstream and LTSSM2 for downstream. So this LTSSM will check the status of the link. LTSSM will check the status of the link and it will also force the link. It will also force link to enter into detect state. Both LTSSM2 downstream and upstream agents will force the link to enter into detect state. So that is known as forced detect state. And we also use this LTSSM2 interface, LTSSM2 agent for getting the LTSSM status. Link bring up whether link is up or down. To know the link up or down to the data link layer state. So we have the LTSSM2 upstream and downstream agents. So next we have LTSSM1 upstream and downstream agent. So this one, so by using LTSSM1 downstream and upstream agents, we will restart the LTSSM. So it automatically enter into LTSSM initialization process. Automatically enter into LTSSM initialization process. So from after resetting the LTSSM, it will automatically progress through all LTSSM states, and we will also use this LTSSM1 and the pipe interface for injecting the errors. See, in LTSSM we have corner cases, right? Like timeout conditions, or if any protocol violation, the state will transition to next valid state. The state will transition to next valid state, or it will come back to detect state. So for checking those all LTSSM corner cases, we have component called adapter. By using the adapter component, we will modify order sets. We will modify order set. We will inject some kind of error in training sequences. So by injecting errors, we can get LDSSM coverage for corner cases. So by using adapter component and error injection sequences, we will achieve LTSSM corner case coverage. And next regarding coverage, so for pipe, we have the pipe coverage upstream and pipe coverage downstream. So by using pipe coverage upstream, we will sample order set coverage. We will sample the order set coverage for upstream, order set coverage for upstream device. By using pipe coverage downstream, we will sample order set coverage for downstream device. In the same way, we have coverage for monitoring TLP types. So we will monitor TLP types, TLP, DLLP. So we will monitor coverage for TLPs, DLLPs, and different sizes of TLP, DLLP. So TLP, DLLP, actual protocol related traffic coverage will be observed in LPIF coverage upstream cover group, and LPIF coverage downstream cover group. So next we have scoreboards. So from upstream and downstream simultaneously, we will start the traffic, protocol traffic, TLLP, DLLP traffic by reusing the same TLP, DLP sequences, and we will coordinate sequences by using the virtual sequencer. So here, whatever data we are transmitting by using TX master upstream agent, same data or same sequence we will use for TX master downstream agent also. So here we are sending the TLPs, and here we are collecting TLP DLLP traffic. So we will compare both transmitter master upstream TLLP DLLP traffic with received RX passive upstream DLLP TLLP packets inside the scoreboard. Same here also. So here we are transmitting and we are receiving DLLPs, TLLPs. So transmitted and received TLP, DLLPs, we will compare inside the LPAF scoreboard downstream component. So here we have pipe scoreboard upstream, pipe scoreboard downstream. So by using pipe scoreboard upstream and downstream, we will compare transmitted order sets and received order set. We will compare transmitted order set, received order sets. Same in downstream also, we will compare transmitted order sets and received order sets using pipe scoreboard downstream. And for sampling the coverage, transmitted order set and received order sets, we have the pipe coverage downstream and pipe coverage upstream. And for sampling the DLLP traffic for both upstream downstream, we have LPIF coverage downstream and upstream. So this is brief about our TB architecture. So we will implement reset sequences for LTSSM, and we will develop different sequences, error injection sequences by using adapter component for achieving the LTSSM corner cases. And next we will develop different sequences for generating TLP, DLP, DLLP traffic with the different lengths, and we will also generate sequences for generating mixed TLP, DLLP traffic. This is about our TV architecture. So next we will see what is the coverage we are going to cover. So this is our TB environment, and it has two interfaces we discussed already. So LPAF interface. So this is the interface between physical layer and data link layer. So LPAF interface, we have LTSM2 agent, TX master agent, RX passive agent. So same way we have pipe interface. It has three interface. LTSSM one agent. So this one will simulate actual pi behavior, electrical pi behavior. So electrical pi behavior, pi electrical behavior, like pi status, and pi. So all electrical pi related signals will be pi status, RX status, TX status. Those signals will be controlled by using LTSSM1 agent, because we don't have electrical pi block here. We don't have electrical pi block here. So TX slave agent, RX slave agent, both will monitor the order set transition. And we have sequence item classes LP, IF sequence item, pipe sequence item, LTSM1 and 2 sequence items. So we will target different sequences. We will develop different sequences. Reset sequence, LTSM1, LTSM2 reset sequence for initiating LTSSM, for initiating the LTSM link training by using the virtual sequence. By using virtual sequence, we will start these two sequences simultaneously on the respective sequencers. So next we have link up one, link up two sequences. And next we have forced detect. By using LTSM2 from the data link layer side, we can force LTSM to enter into detect state. And we will develop different data transactions for different TLP lengths, and DLLP packets, different DLLP packet lengths, and mixed, both TLP, DLLP mixed traffic. So we will create broadly three type of data transmission sequences: TLP sequences, data link DLLP sequences, and TLP DLP mixed traffic sequences. Next, we will also focus on error injection sequences by using the adapter component, mainly for achieving the LTSSM. For adapter, by using adapter, we will inject the error injection sequences for achieving the LTSSM corner cases. For achieving LDSM corner cases, so we will use error injection sequences. So we have these agents: TX master agent, RX passive agent, RX slave, TX slave agent, LDSM1 and 2 agents. So these all we discussed as part of the TB architecture, and we will implement scoreboard. Total we have four scoreboards, two for upstream and two for downstream. And we will develop a coverage model. So before that we have adapter component. So this one is non-UVM component. So adapter work in two modes. One is error injection mode and another is packet bypass mode. So if we enable error injection mode, so it will inject errors based on the error injection sequences for controlling the LTSM state transitions. So these are the cover groups we are developing. So this is for LTSSM downstream devices, LTSSM downstream devices, LTSSM transmit downstream device cover group. So this one LTSSM transmitter downstream receiver cover group, and this one LTSSM upstream transmitter cover group. See here we covering detect active to polling active to polling configuration, polling active to poll detect. So this is corner case. Uh, so this is corner case. So this we will achieve by using error injection sequence. Next, polling configure link with start to link with accept to lane with wait. And from link with start again we are going to detect state. So this one also corner case. So these corner cases we will achieve by using LTSSM. Sorry, by using adapter error injection sequences. So this one is for upstream upstream RX LTSM upstream RX coverage group. This is a transmitter downstream order set cover group, and this one a receiver downstream order set cover group, and a transmitter upstream order set cover group, receiver upstream order set cover group, and so we are also creating cover groups for uh, getting coverage. Sampling coverage for TLP packet, DLLP packet with different size, minimum size, maximum size, and for different length and different sizes, we are sampling TLP, DLLP coverage. So this is for downstream device. So this one is upstream RX data, upstream RX TLP, DLLP cover group. So this one upstream TX, TLP, DLLP cover group. And final one, this one upstream. So upstream RX, TLP, DLLP cover group. So these are the cover groups we will create in this project. So for achieving coverage, so total we are getting around 90% coverage. So we are achieving around 90% coverage. Yeah. So this is about our coding PCIe functional verification of Mac layer. So regarding further questions, you can join in demo class. Yeah, thank you. Thank you all.